welcome to the lecture series of optical instrumentation. My name is Sharad Gupta and this is lecture number 4, and in this lecture we will discuss polarization and birefringence, that is double refraction. Okay. So, first let us discuss about polarization. So, polarization is a property of wave that can oscillate in more than one orientation. So, a normal light ray, in normal light ray, the particle of medium vibrates perpendicular to the motion of light and in all the directions. So, magnetic field vector or electric field vector, it vibrates in all the directions. So, for example, if a light ray is coming out of this screen like this, so if a light ray, for example, this is a light ray and it is coming out of this screen like this, so electric field vector will vibrate perpendicular to the motion of this beam and in all the directions like this. Okay. So, if light ray is coming is moving in this direction, so electric field will vibrate like this, like this, like this in all the directions. So, if this vibration is somehow converted only in one plane, So, now this wave is coming out of this screen and the electric field vector is vibrating only in perpendicular plane. So, such light ray is called plane polarized light, and the process of converting this unpolarized light into plane polarized light is called polarization. So, it is a property of wave that can oscillate with more than one orientation. A light wave that is vibrating in one plane is called polarized light, okay, and a light ray that is vibrating in more than one plane is called unpolarized light. Okay. So, this is a polarized light ray, and this is unpolarized. Okay. The process of transforming unpolarized light into polarized light is called polarization of light. Like over here it is shown in this diagram. This is a non-polarized light, light is travelling in this direction, okay, and the vector is vibrating in all the direction. This is a Polaroid. What is a Polaroid? Polaroid is a substance that can stop this vibration of all the planes and it will allow the vibrations of a single plane to pass. Okay. So, when light passes through this Polaroid, only the vibrations that are in this direction, perpendicular direction, they will pass. So, this is a polarized wave, this is unpolarized, non-polarized wave, and if there is a Polaroid of perpendicular orientation with comparison to the earlier one, then no light will pass from beyond this point. All the light will be stopped by this Polaroid. Why? Because there is no part of the vibration that is in horizontal axis, the vibration is only in perpendicular axis. So, it only allows the vibrations in horizontal direction. Okay. This is another diagram, this is one more diagram. Okay. It is taken from internet. Again, this is a light ray, ordinary light ray, unpolarized light ray of intensity S, and this is a vertical polarizer. When the light ray passes from this polarizer, now it is polarized light and the vibrations are only in this direction. The intensity is reduced to half. And if we keep another polarizer with 90-degree angle from this earlier one, then all the light will be stopped. And if there is a certain angle, then the intensity will be calculated by this formula, that is Malus law. Okay. So, now the types of polarization. Mainly there are three kind of polarization: linear polarization, circular polarization and elliptical polarization. What is linear polarization? This is the diagram that shows linear polarization. So, from this direction unpolarized light is coming on these polarizers. So, this is a vertical polarizer, this is a horizontal polarizer. So, what it will do? It will only allow vertical vibrations to pass. So, the vibrations that are in blue color, they are passing. So, this is plane polarized light, vertically polarized light, okay, over here, or we can call it linearly polarized light. Again, this is in 90-degree, the orientation of this polarizer is 90-degree. If we compare it with this one, then it will only allow vibrations that are horizontal, that is red color vibrations. So, this is also, this is horizontally polarized light and also linearly polarized light, okay, like this. This is horizontally polarized light and this is vertically polarized light. This is the orientation of polarizer. We call it horizontal polarizer, we call it vertical polarizer. So, if we rotate it 90-degree, it will become horizontal polarizer, or if we rotate this one 90-degree, then it will become vertical polarizer, okay. And over here, this is how we show unpolarized light on plain paper, right. So, this is electric field vector vibrating in multiple directions as shown in this 3D diagram, okay. So, this is called linear polarization. Next is circular polarization. As you can see in this diagram, the electric field vector is rotating, so it is called circular polarization. And in elliptical polarization, it keeps on changing. So, it looks like an ellipse and their combination is considered ultimately. So, it looks like elliptical polarization. So, this diagram shows elliptical polarization. Now, polarization by reflection. When unpolarized light is reflected, then we get polarized light, and we will see this in details. Polaroid sunglasses are familiar to most of us. We all know what are Polaroid sunglasses. They are used to reduce the glare. They have a special ability to cut the glare of light. Now, what is glare? When light is reflected from surface, from different surfaces, then we get glare. Either it is reflected from glass or it is reflected from water. Polaroid glasses are used to reduce this glare. You can check this by yourself by holding Polaroid sunglass in front of you and rotating them while looking at light that is reflected from any surface. Like this, in this example, you can see there is a water body, there is a river or lake, and the light, you can see that the light that is reflected from this the surface of the water, it is showing clouds over here. These are clouds. Okay, so this is called glare, and due to this we cannot see the bottom of this lake. These two photographs shows photographs of a river show the effect of polarizing filter. So, over here we have taken this image by using a Polaroid glass. So, Polaroid glass has reduced this glare. Why? How? We will discuss later. So, part A is without polarizing filter and part B is with polarizing filter. Similarly, over here look, this image is taken without using polarizing filter. So, there is reflection from this glass. So, we cannot see anything that is inside, we only see the reflection, but this image is taken using a polarizing filter. You can see all the reflection, all the glare of light is removed using this polarizing filter. Photographs taken of a window with a camera, polarizer filter rotated it to two different angles. In this picture, the polarizer is aligned with the polarization angle of the window reflection, and in the picture B, the polarizer has been rotated 90 degree. So, it has removed the glare. Polaroid sunglasses cut the glare in reflected light because that light is polarized. It cannot be completely blocked by a polarizing filter because the reflected light is partially polarized. When light is reflected from a surface, transparent surface, either glass or water, it is partially polarized, and we can use a polarizing filter to remove that reflection. So, if we remove that reflection, the glare is reduced and it helps in improving the vision, okay, or it also helps in improving the quality of photographs like this. So, we have seen that reflected light is partially polarized, but there is certain condition, and through that condition reflected light can fully be polarized, and this condition we will discuss here in Brewster's law. If light strikes an interface such that there is a 90-degree angle between reflected and refracted rays, then the reflected ray will be or is linearly polarized. We know that if light falls on a transparent surface, some light is refracted, enters the medium, enters the surface, and some light is reflected back. So, what is Brewster's law? According to this law, if there is 90-degree angle between reflected and refracted ray, then in this condition the reflected ray is linearly polarized. Over here, through this diagram we can understand this. So, this is unpolarized light, incident light ray, this is glass, this is again air. So, some of the light will enter the glass, some of the light will be reflected back. So, according to Brewster's law, if this angle is 90-degree, right angle, angle between reflected ray and refracted ray, then in this case this reflected beam will be linearly polarized, okay. And the direction of polarization is parallel to the plane of the surface. The direction of polarization, it will be parallel to the plane of the surface. The spatial angle for which we get a 90-degree angle between reflected and refracted ray is called Brewster's angle, okay. It is called Brewster's angle or angle of polarization. So, if we make the light ray fall on the glass plate at this particular angle, then we get plane polarized light, linearly polarized light. So, we call it angle of polarization. So, the tangent of angle of polarization is numerically equal to the refractive index of the medium. The tangent is equal to the refractive index of that particular medium. We will see this using small derivation. So, let unpolarized light incident at an angle equal to the polarizing angle. So, let us consider that this is polarizing angle and we are writing it as theta b, okay, theta b, Brewster's angle. So, in this case what is, according to Brewster's law, refractive index of glass mu is equal to tan into theta b, okay, or we can also we have written is incident angle tan I. We can write it as sin I upon cos I. And we know from Snell's law, refractive index is equal to sine of angle of incidence divided by sine of angle of refraction, sin I upon sin R. So, by comparing these two equations, we will get sin I will be cancelled. So, cos I is equal to sin R, cos I is equal to sin R, or we can also write it like this, sin R is equal to, we can write cos pi by 2 minus R, okay. So, I plus R is equal to pi by 2, angle of incidence plus angle of refraction is equal to pi by 2. So, according to this law, according to this law, I plus R is equal to 90 degree. What is, where is angle I? This is I and this is angle of refraction R. And according to law of reflection, we know this angle is equal to this angle. So, this plus this is equal to 90 degree. It means this plus this, R plus I is equal to 90 degree, pi by 2. So, again this is a normal. So, this is 180 degree. So, 180 minus 90 is equal to 90. So, this angle is 90 degree. Okay. So, this is Brewster's law, and if the light ray is incident at this particular angle, Brewster's angle, then we get plane polarized light. Next, another phenomena that we have to discuss in this lecture is double refraction or birefringence. So, what is double refraction? It was observed by Bartholonus in 1669. 1669, 9 years after Newton proposed particle theory. He proposed particle theory in 1660. Okay. So, how did he observed this phenomena? He placed a crystal of Iceland spar, that is calcite, above some words written on a paper, and he obtained two set of images. So, he obtained two words like this: a calcite crystal, it is placed upon a graph paper. So, what we can see, we can see two images, we can see parallel lines, we can see two images through this calcite crystal. So, why it is so? It is due to double refraction, birefringence. Okay. So, double refraction, what is double refraction? There are several crystals like calcite that have double refraction properties. In this case, when unpolarized light beam is incident perpendicularly on the crystal, two refracted rays are formed. When unpolarized light comes normal on this crystal, calcite crystal, then two light rays are formed. One is called O ray, another is called E ray. One is called ordinary ray, that is O ray, and another one is called extraordinary ray, we call it E ray. Why these names are given? Ordinary ray is the ray that follows Snell's law, that is why it is called ordinary ray. But another ray, it does not follow Snell's law. So, that it is why the name is given is extraordinary ray, E ray, because it obeys the normal laws of refraction or Snell's law, and another ray does not follow Snell's law. So, as in this diagram we can see a light ray is coming on this surface. This is crystal's optical axis, this is a crystal of calcite. So, light ray is getting refracted and two rays are produced, one is ordinary ray, another is extraordinary ray. So, it is observed that these two rays are plane polarized and their plane of polarization is mutually perpendicular to each other. Okay. It was soon discovered that these two rays were totally plane polarized at right angle to each other, So, as we can see in this diagram, one second, as we can see in this diagram, these two rays are plane polarized, completely plane polarized, and the plane of polarization in this electric field vector is vibrating like this, and in this it is vibrating like this, mutually perpendicular to each other. Okay. So, this is double refraction, and we can use this phenomena to construct an optical element that is used as a polarizer, and it is called Nicol prism. So, how do we do it? If we can somehow separate this O ray and E ray, then we can get single ray, that is plane polarized light ray. So, how do we do it? If we could separate the rays, then we would have a very good method of producing polarized light, because calcite is a very normal substance, it is available very easily, very cheap. Okay. Otherwise, polarizing filters are costly. So, Scottish physicist William Nicol found a method and devised Nicol prism in 1828. He made this Nicol prism in 1828. What did he do? A crystal of calcite cut through the center and then stuck together again with a glue, a special kind of glue called Canada balsam. What is the name of that particular glue? Canada balsam. So, over here, this is a whole calcite crystal, it is cut along this axis and again pasted again using a glue Canada balsam. What is the importance of this glue? Why this specific glue? Because the refractive index of this glue is such that the importance of the glue is that its refractive index is less than that of calcite for ordinary ray and greater than calcite for extraordinary ray. Its refractive index is less for ordinary ray and greater for extraordinary ray. So, what will happen? Extraordinary ray will enter easily in this glue and ordinary ray will not enter due to the process of total internal reflection. Now, what is total internal reflection? When light ray falls on the surface greater than, at an angle that is greater than critical angle. For example, let me explain total internal reflection. This is a surface, this is air, this is glass, normal. If light ray is going from denser medium to rarer medium, it will move away from the normal, and if this angle of, we keep on increasing this angle of incidence to a particular angle called critical angle, then this light ray will go like this and this is called critical angle of incidence. And if we further increase this angle, then for example, if we have further increased this angle like this, then this light ray will go again in this direction, and it is called total internal reflection. This is the process phenomena through which a light propagates in optical fiber. Okay. So, using this same concept, what it will do? So, the refractive index of Canada balsam is less and this part is more for ordinary ray. So, what it will happen, this is normal. So, due to total internal reflection, this light ray will come here and the E ray will pass. So, we get plane polarized light ray here, plane polarized light ray here. So, we can easily construct this Nicol prism to get plane polarized light, and this is a very good and efficient method. Okay. This means that the total internal reflection can and does occur for ordinary ray, but not for extraordinary ray. Okay. So, this was all about polarization and birefringence, that is double refraction. Thank you.